Okay. First, good morning and thank you for attending this talk and the organizer for accepting my presentation. I would like to introduce this talk, which is a work in progress. It's not finished yet, but it's taken several years. It's a course-based undergraduate research experience, like it's known as a student for biochemistry majors in physical chemistry. Let me just a brief overview of what I want to talk with this presentation, a brief context in Uruguay about the physical chemistry for biochemistry majors. Our idea was to give a physical chemistry course that is directed specifically for biochemistry. So most of the examples that we use and the experimental activities are related with biochemical molecules. Which other institutional policies are given for a student for their first research experience that we have in our university? Then we will see a bit about what the American Chemical Society and the International Union for Biochemistry and Molecular Biology has as objectives for the teaching of physical chemistry. And let's talk about models in physical chemistry, because chemistry is much about models. And then why we think that the CURE platform should be useful to propose an experimental laboratory in physical chemistry for biochemistry undergraduates. And later the objective of the specific course, the proposed course, and conclusions and final remarks. Okay, a brief context in Uruguay. For biochemistry majors, physical chemistry has a strong content in the career. We are in the third semester with the topics of thermodynamics and formal kinetics, but previous knowledge in general chemistry, mathematics, physics, biology, and analytical chemistry. And later the students continue with quantum chemistry, electrochemistry, colloids, and biological physical chemistry. So the content in physical chemistry overall is quite strong. And you can see PAIE. PAIE is a student research support program that is financed by our university, in which students are selected to develop some kind of research experience, the first research experience before the thesis, and they are given around 500 to 1,000 euros in order to work in this first experience. But also implies a selection of the students to do this. Okay, according to the American Chemical Society and the International Union of Biochemistry and Molecular Biology, the topics that should be taught in a physical chemistry course for biochemists includes macromolecular structure and function, thermodynamics, calculation of thermodynamic functions, applications to metabolism and protein structure, equilibria, and rate law. And the American Chemical Society specifically put as topics in thermodynamics, some of them with more details, as you can see in the slide. So for thermodynamics and for kinetics. So we try to include all this in our course in order to fulfill all these requirements of this desired course. In the objective for teaching physical chemistry, these two associations also provide some cues about this. And I want in black you see something that we want to point out is the use of models that is key in physical chemistry. So, for example, one of the objectives is to provide mathematical models or introduce microscopic models and qualitative, quantitative models and develop models. It is important to introduce to the students the assumptions and limitations of models, for a model can be validated or not. What does it mean to validate a model or do not validate a model? So in this context, the use of models, which kind of models can we use in physical chemistry? The first time, we have three possible models. Models based purely on a mathematical equation, just a relationship between two properties, as mathematical relationships, and nothing else, no extra meaning. This model. A model that is based on physical rules, or a model that is based on theories. So let me talk a bit more about this model. And we have a model based purely on mathematical means. We have, for example, let's see the second one, the extended virial equations. They are just polynomials that we allow us to relate two measurable properties in an equation with no physical mean for each of the parametric constants. It's just an equation. Other kind of equation that is known as linear extrapolation method, that's seldom used in biochemistry, allow us to calculate the Gibbs energy of the unfolding process of the protein. It's just with varying concentration of CDA, this nascent form that induce the unfolding process. We just change the concentration of the unfolding agent, and we measure the equilibrium constant, so we can calculate the Gibbs energy, and we can extrapolate the standard Gibbs energy that cannot be measured directly because it's possible. So the constant M has no physical meaning. It's just that we know that the Gibbs energy follows a straight line with the concentration agent, but it's useful. We can obtain the Gibbs energy. Other models that are based on physical means, they are known as laws. We don't know how to demonstrate the laws, but the laws exist. First and second laws of thermodynamics are examples of that. Axiomatic, we cannot prove them, but there's a lot of science that demonstrate that they are valid. And others are based on theories. And for example, a Van Hoff analysis of equilibrium constants with the temperature, or Eigen analysis of kinetic constants with temperature. We do some mathematical transformation and we use these models. We can obtain by calculation some specific properties. For example, the enthalpy of a reaction of a process, but only if the model is verified. But what happens if the model is not verified? What can do the student when they cannot verify this model? But this is one of the questions that we want to address in this presentation, because usually in the experimental approach that is used in many universities, the experimental part is consisted in a series of unrelated laboratory practices that they are usually used to demonstrate the validity of a given model. So they never have the chance to analyze what happened to a system that do not verify such model. And this is what happened in our daily life in research. Models are not verified. So this pedagogical is as important to verify a model than to verify that this model is working and to arrive to the correct conclusions. So why we think that Cure platform or Cure methodology is useful to be used in a physical chemistry laboratory practice in order to give some uncertainty to the experiment that students are going to perform. For example, the 5 key elements defining a curve, you can see it in the slide. It's always related to engaging students in scientific practices, emphasizing collaboration, examining broadly relevant topics, exploring questions of unknown answers, this is very important, and integrating interactions into the course. So, what Cure can is benefit for a student, for example, that there is no the student selection. Remember, I told you the program that exists in my university implies a selection of the students. Here, there's no student selections, and all the students have the opportunity to be engaged in a research experience, and they earn course credit, which is important for the advance in the career. But I would like to point out some other benefits of Cure. That research results are unknown for the student and are unknown for the teachers, for both. No one knows what's going to be the result. A wider experimental choices to conduct a research, which implies that the student has to pre-research which measurement has to do, which is the experimental procedure that is going to take. Everything they have to research previously before conducting the experiment. And the uncertainty on the model by validation, which is one of the things that we want to address. What happened with Cure and chemistry? Well, as you see there, Cure has more or less 10 years in developing, and chemistry is, as a discipline, had an intermediate interest in Cure methodology. You can see that in orange, that Cure is in the middle of the table within the different disciplines, and in the pie graph, you can see that within chemistry, physical chemistry is only has one paper published in all this year. And if you read this paper, you see that it's for a secondary level physical chemistry course. So they need that all the basics of physical chemistry known before access to this course. So, up to our knowledge, this will be the first proposal for an undergraduate physical chemistry in the Cure methodology. So, which is the objective? Is to introduce students to experimental scientific research in the context of an undergraduate physical chemistry course for biochemistry majors, using a specific topic as an example to reach a comprehensive conclusions. Which is the specific topic that we want to share for biochemistry students? Is the study of a protein and the native conformation, how to measure the concentration, how to measure the properties, and so the system from a dynamic point of view would be the protein, the ambient would be the surrounded water, and the process that we are going to study is this ensemble of the protein, so the unfolding process of the protein. With this, only this, we can present a whole course covering all topics that we want to cover in thermodynamics and in kinetics. And what are the design skills that we want to develop? Is the possibility that the students have experimental design by their own, the selection of experimental procedures, the application of models and their experimental verification, yes or no, and the analysis of the results to give a global vision of the thermodynamic process that we are going to see later. And the pre-requirement are the pre-requirement we have now in the course. There's knowledge in mathematics, physics, general chemistry, and analytical chemistry, and measurement laboratory and error analysis. Which is the proposed course for a one semester. It consists in 8 laboratory practices, including protein extraction, analytical concentration measurement, protein structure from PDB files, kinetic of chemical denaturation, the kinetics of thermal denaturation, the chemical induction of the protein denaturation, the thermal induction of the protein denaturation, differential scanning calorimetry, and Gibbs energy of transfers of peptides and amino acids. All this practice fulfill the conceptual topics required by the ACS and the Association of Biochemistry and Molecular Biology, as you can see in the slide. So let's have a brief look at our proposal and why we think that the needed flexibility and the fact that we don't know the final result of the research is, for example, in improved protein extraction and analytical concentration, they can extract, for example, the protein with different materials, different buffers, in different conditions, with the addition of or not of different agents, and they have to choose analytical measurements according to what they are going to measure, and kind of spectroscopy. They have to determine the linear range of their properties that they are measured. So this is the main option of this practice. In the protein structure from PDB files, knowing the protein that they're working with, they can go to the PDB files and look at the molecule and see which are where the hydrophobic amino acids are located, where the amino acids are located, the known hydrophobic pockets, for example, and have an idea of which kind of intramolecular forces define the native structure of the protein. In the kinetics of chemical denaturation, of thermal denaturation, they study a kinetic of the kind of reaching an equilibrium between the native and the natural form of the proteins, and they can obtain the sum of the microscopic content, and the most important, they know what is the time to achieve the chemical equilibrium, because they will need this for the practices in LP5 and LP6, in which the protein, the process of unfolding is induced by a chemical agent or the temperature. They know how long they have to leave the system to reach the equilibrium, to make the measurement that they would reach the equilibrium constant of this. And from this practice, they can calculate the Gibbs energy in one of them, and the enthalpy and the entropy of the unfolding process in the other, and then they can see if delta G equals delta H minus T plus delta S is fulfilled, and if it is not fulfilled, they have to try to understand why it's not. It's always there is an intermediate that's not allowed for the accomplishment of this equation. With their own results, experimental results, they can go to, we don't have for students the differential time calorimeter, but an Excel spreadsheet that they can provide, they can calculate the profile, the temperature profile. So with their own results, they can construct the thermal profile of the unfolding process. And finally, based on the structure they found, they look at in the PDB files, and depending on what we have in the laboratory, the reactives, they can determine the Gibbs energy of transfers of different amino acids of different peptides that they found in the structure, trying to understand why they are in the core of the protein or why they are in the surface of the protein. What do we give to the students for this? This is not, we will give them a protein or a source of protein. So we cannot give them a specific paper to read. We have to give them literature wide enough to understand the procedures, and then they have to adapt the procedures for their specific sample. So in methods and in enzymology, why there? Sorry, they have some papers describing these methods in a wide form that suits improve that suite very well what they are doing. And there are two web pages. One is related with the thermodynamic properties of some proteins, and the other is the PDB5. So they can choose and they can look at this confident source for some data. Okay, as a final remarks, I told you that 6 years we are transforming our physical chemistry course to teach a course that is specific for biochemistry measures. So because we found when we began, we found that biochemistry students didn't like to make calculation with the sodium chloride, magnesium chloride, and they want proteins and analysis. Unfortunately, the literature is much poorer in these examples. So we made this course for many years, and we took two lines. One is to working with biochemical substance is expensive. So we need to scale all laboratory. Now our laboratory, we have 30 students per year in the semester. The whole cost of this laboratory is below 50 euros for the whole semester. So we go down the prices a lot. And we work in a micro-scale laboratory. What kind of things that we do for lowering this cost. And the other thing that for chemical students, the chemical reference state is that, but for biochemistry students, the biochemical reference state is that. And unfortunately, the textbook in physical chemistry do not introduce the biochemical reference state, that it is not pH 7, it's much more than this. And it was proposed in 211. Not many books provided. So we teach, we make some papers introducing biochemical thermodynamics and how to teach physical chemistry in the context of the reference state of biochemical thermodynamics, including one of them that is my favorite, is the one in the right, that is the confidence source of data for students. They have to choose data and they Google everything that they're in Google. So how to look for confident data that they can use. So just want to introduce you to the building of cognitive science and the staff in the laboratory. I'm sorry for my English. Thank you for your day.